that was quite an intro. By the way, Zdravo Skopje, ja sam Matheus. And that's all Macedonia got of today, sorry. But let's talk about thinking outside of the box. Again, this is me. You can find me everywhere as Y Combinator. I'm a staff software engineer at this company called Medallia, and I'm a GD in web technologies. And I'm also the one thing standing between you and lunch. So I hope, be patient with me. Before we talk about the two topics we have today, I want to run a little bit of a preamble as to why I even had the idea for this talk. And I'll start with a take that's probably not a spice take at all, but in my opinion, I think we do have a lot to learn from other tools. No matter what you're doing, Angular, React, backend, I think we have to. And my first evidence for this is this tweet by Dan Abramov from 2021. Who here works with React, by the way? Yeah, so probably, I would say 60% of you, so you know who I'm talking about. Dan Abramov is the creator of Redux and also one of the core team members of React. And back in 21, he was basically saying how a lot of the things that frameworks were doing in 2020, Marco by eBay was doing since 2014. And he linked this post from 2014 from eBay's engineering team. And this post was talking about progressive HTML rendering. The fun thing, though, is that this post by eBay linked to another post by Jeff Atwood, aka core founder of Stack Overflow. And this post was from 2005, and he was talking already about progressive HTML rendering in .NET in this case. So I think this connects to the fact that we do have a lot to learn from the past too, as we saw in Salma's talk. And case in point, this post by Vercel from 2023, they were announcing partial pre-rendering. And one of the first paragraphs shows how a lot of that grabbed inspiration from the 90s. More specifically, they were talking about server-side includes, which is something that's been around since '93. Moving forward, I also do think that we have a lot to learn from other industries, like the game development industry. Case in point, another React post, yeah, I'm a little bit biased React-wise, but this is Andrew Clark, another core team member of React and one of the minds behind the concurrent features of React. And in 2018, he was talking about how a lot of how React works underneath, like the model of having 2 trees, work in progress tree, current tree, and all of that, was grabbing inspiration from a technique that's been around in the game industry for a while called double buffering. Or you'll find some references to it as multiple buffering. And stretching a bit, I think we also have a lot to learn from other countries or other parts of the globe. And yeah, that's a Ryan Carniato reference, if you're a friend of mine. Yeah, there's this post by Ryan Carniato. If you don't know him, he's the creator of Solid, and he used to work at Marco team too. And he was talking about what Marco was cooking up back in 2021. But what caught my attention in this post was actually a comment in the thread. But this Chinese guy, his username was Yasar, and he was basically saying, yeah, that's some cool stuff you're talking about, but including SSR and stuff, but in my country, we just do things differently. And he's talking about the constraints and how they build apps in China. And this, back in 21, plus the fact that throughout the years, I saw really good talks by the members of ByteDance, like Juan, who is one of the main persons behind Lynx, and Zach Jackson, the creator of Module Federation. So watching these talks for guys working for ByteDance like TikTok also showed me that, oh my God, I have so much to learn from them. So that's exactly what we're here to do today. I want to talk about things I've learned from how people build apps in China and things I learned from how people build games. And we'll talk about mini apps and super apps and also something called ECS from the gaming industry. And for both, I want to run like a little bit of my history with that, an overview of the architecture, the ecosystem, and a little bit of why I think this matters at all. No further ado, mini apps and super apps. And going super quick, my history with that actually started in 22 when I was exploring a lot the Great Firewall of China. and how it could impact the way that the web app I was building could even load in China. And it's a huge rabbit hole once you start exploring that, because they employ a lot of different network techniques, including this thing called deep packet inspection that can actually result in a lot of loss for your CSS, JavaScript, and other models. And I started exploring more and more the limitations, the restrictions, and also how they were even building apps to begin with in there. And a little bit of an overview about super apps. So as the name suggests, those are hosts to other apps that runs within them, and they basically dominated the whole Chinese market. And you probably heard some of these players like WeChat, Alipay, Baidu, Douyin, which is the Chinese TikTok, and TikTok itself. And to bring in some numbers to what I'm talking about, these are not even the users they have, it's just the users of the mini apps. So WeChat has about 900 million users using their mini apps, and Alipay, which is another mini app ecosystem, has around 661 million users. And all of those has total users about 1 billion or even more, China scale. And this is what those mini apps look like. They run within the host app, and they basically are used for everything: messaging, streaming, games, e-commerce, ordering food, and whatnot. But I want to talk a little bit more about the architecture, because they have some very, very interesting aspects to it. The first thing is that most of them share a dual-threaded model where you have a view layer and a logic layer. So the view layer, as the name suggests, only deals with rendering stuff and listening to things coming from the logic layer. And the logic layer processes data, receives data, processes, and sends over back to it. And the first takeaway from that is because the view layer is never blocked by long-running tasks from the logic layer, as opposed to what we've seen a lot in the web apps we've built. So illustrating a little bit, that's it. In the view, you mostly have a web view that also employs some native rendering. And then on the logic layer, you have a JavaScript engine that can vary depending on which platform we're talking about. They all bridge to native APIs, and those also can communicate with the mini apps or with the super app server via HTTPS or WebSocket, depending on what you're building. Also, the view layer on iOS, it mostly uses WebKit WebView. So if you build native iOS apps, you probably know this. And on Android, they have different proprietary engines. Like two examples are X5 by Tencent and T7 by Baidu. And in their own DevTools, because they got their own IDEs, DevTools, and whatnot, they run on Chromium. The logic layer on iOS, that's mostly JS core. And on Android, that's V8 or a variation of it. And DevTools is going to use something like Electron and Double.js, or one of these alternatives for delivering Node apps to the desktop. When it comes to execution, that's really interesting, because if you check a list of popular rendering engines, you will find Blink, you'll find Edge, you'll find WebKit, all of those we already heard of, but you'll find T7, U2, X5, U3, T5. If you ever check the list and wonder what those are all about, those are those engines belonging to the mini apps ecosystems. So talking a little bit more about the view layer, the first thing to discuss is templating, because there's usually a markup language that looks like HTML, but it's proprietary, and the runtime of the mini app is going to translate that into HTML or native code, depending on which components you're using and stuff. And another thing is that each page that you navigate across a mini app is going to spawn a new web view, but they do optimize some of things like having a shared cache for that web view and stuff. And another thing, as I mentioned, they all got their own languages. So for example, WeChat is called XML, Alipay is AXML, Baidu is called Swan, and for ByteDance it's called TTML, that if I had to guess, I think TT has to do with TikTok. And that's one example of what it looks like with XML, and you will find a lot of similarities. For example, if you've done Vue or any other thing that looks like Vue or these templating languages, that's a if then else block, for example, that you see on the left, and you can inject some data in the page object. Speaking of which, by the way, a lot of this talk is about establishing parallels between what we have now and what we've had throughout the decades. So you'll see a lot of similarities to what Vue has been doing for a couple some years now. But if you've done Mustache or any other template system, you will also relate to that. And that's something that's been around since 2009. But even more, actually, client-side templating like this has been around since '98 with this thing called XSLT. Speaking of talking about the past, the way that a lot of these apps is organized is also they do MVVM, which stands for Model View View Model. So if you were building native apps about 10 years ago, for example, you probably heard of that. And they all have components. So they all have a bunch of built-in components. And by the way, the screenshots of the documentation are in Mandarin because that's, for most of them, the only language you'll see them documented. And you can also create custom components for them. Moving forward and talking a little bit about the logic behind it, just like they have their own versions of HTML, they also have their own versions of JavaScript. So XXS, SJS, and so on. And they're all subsets of JavaScript. For example, for security reasons, they don't support eval, they don't support creating a function with the function constructor, because you're not on the web per se, you don't have done APIs like document or window. A lot of times you don't have ES modules. But some of the ecosystems, they will provide polyfills for you out of the box. And they will enhance that with a bunch of APIs for interfacing with the native layer. So that includes accessing file system, geolocation, camera, and a bunch of other things. And they also even have APIs for you to figuring out if an API exists. So the measure for example, they got an API called CanIUse, which I think is inspired by caniuse.com. And you can pass a path and an API to see if that's available and use that. Last but not least, styling. You have some, for styling, again, dialects, this time dialects of CSS that are mostly changed to add responsive pixels. So they introduce units to basically figure out a lot of responsiveness for you out of the box. And they support importing things with the add import rule, and you can also declare them in line in your template, so that means that all the niceties of the template engine you can also use, like interpolating. My favorite technical part about this, though, is talking about performance, because some of you may have the impression that they are lost in time by implementing their own versions of pretty much everything. But they actually, at the same time, do a bunch of the cool stuff we've been doing in our communities. One example is this thing they call snapshots. So it's about pre-rendering. They pre-render some pages of your mini app in the cloud of the host native app, and they generate an intermediate compressed representation, and then the engine running in the mini app within your device is going to load, parse, and render that snapshot, giving you faster access to the key pages, for example. And that means going, for example, a 50 kilobyte source of JavaScript to a 3 kilobyte snapshot. Another thing is Virtual DOM. So Virtual DOM was quite a hot thing for the front-end community for a while. And they also, a lot of these engines, they employ Virtual DOM, and they even enhance it with WebAssembly, for example. And they also move a lot of the heavy stuff to WebAssembly, and they patch the JavaScript engine to communicate the bridging, which is, if you've done anything in the browser with WebAssembly, sometimes bridging the DOM to WebAssembly, there's a communication cost, but they also improve the engine to address this. And last but not least, they also have this thing called Skyline in Glass Easel. This is a WeChat thing, which is basically their newer rendering engine, and it's meant to be faster and more efficient than the traditional web view-based engine. For example, if you've done any mobile, you probably rolled up your eyes when I mentioned web views. And this one is replacing the legacy architecture with a very, very much streamlined version that tries to achieve native-like performance. So they also ship with their own native component system, which is this thing called Glass Easel, and all the traditional browser stuff like layout and styling, compositing is moved to this new engine. And another thing is that they share just one instance of that rendering engine instead of spawning web views for every page like we talked before. One of the most interesting things, though, about that is that they enhance with some things. like this concept called worklets. So worklet basically denotates with the compiler pragma any code that can be ran on either thread. And what's interesting about this is that then they have functions like run on UI or run on JS, and you can actually send code over across the JavaScript and the UI thread. And the reason why I'm highlighting all of that to begin with is you probably saw similarities when I showed this work notation to what Next.js does in the app router, where you have use client and use server to denotate the boundaries. But not only that, they also employ that to denotate infrastructure with things like use cache. And it's not only Next.js that does this. SolidStar, for example, has use server and similar notations for that. And going one step further, even Lynx, the new competitor to React Native by ByteDance, they also have this background-only notation that also tells where to run your code with a similar compiler pragma. So that's this techniques and knowledge happening over the years across different implementations. One of the last things is ecosystem-wise. Basically, there's a lot of open source you will find about this. You're probably wondering if this is something really close and there's nothing on GitHub. So WeChat and other companies, they just got a lot of open source stuff for interfacing with React, for debugging tools, and a lot of other things. And this stage is all about the web as a platform, right? So there's also the Chinese Web Interest Group, part of the Web Consortium, or W3C. And not only this, since 21, there's also a committee working dedicated on standardizing the patterns behind all of that. And this committee has members from all of these companies we talked about, including Alibaba, Baidu, ByteDance, Huawei, Intel, Xiaomi, Facebook, Google, and a lot of these. And they even got in-progress white papers to document a lot of things, including manifests, packaging, distribution, and a lot of stuff. Other than this, you'll see mini apps in different hosts too. So who here uses Telegram? So I thought I'd see more hands. So Telegram, they also have an open mini app ecosystem that doesn't work precisely the same way the Chinese one does, but they do have open source that you can use to create your own mini apps to run within Telegram, and even other hosts from other countries. So VK, which is a very, very popular messaging app in Russia with millions and millions of users, they also have a mini app ecosystem with almost 1,000 mini apps available, and they also have a lot of open source for creating mini apps. And by now you're probably wondering, why does this all matter? So besides the numbers I talked about, I want to say why it matters to me. So there's a lot of research showing how you can better reach out people in specific parts of China or in China as a whole with that, and the successful rollout of different mini apps. If you saw my bio, I work at Medallia, which is a CX company. And I work a lot with surveys. And there's this one paper that I read the other day that is about rolling out mini apps to countryside parts of China and how they managed to get a 98.2 response rate in the surveys that they were running. And if you work with CX and if you work with surveys, you know that if you get a 10% or a 15% in response rates of any survey, you should already be happy. So I really like how mini apps can be about delivering the right message to the right audience across the right channels, depending on what you want, of course. But I do have to do a little bit of intermission here because this is past half of the talk, and I promised we were here to discuss about learning from other industries too, not only other parts of the globe. And who here has heard of React Fibers? Okay, some of you. And who here has heard of Effects? Yes. Okay, same people. So React Fibers was this major rewrite of React that was announced in 2017 of the whole way how React works under the hood, and a lot of it was based on fibers. And Effects.js, which is a very, very popular framework these days, has also a lot of its foundation on the concept of fibers. I'm not here to describe what fibers are, but it's funny to see how they've been around for quite a while now. We just started listening about it. For example, Windows XP had them available for you to build apps with, and Windows Server 2003. And you know where else you could find fibers? In this talk by this guy, he was talking in 2015 how he is an engineer at Naughty Dog, and he was talking how he optimized the performance of The Last of Us in the PlayStation 4 using fibers 10 years ago. And this reminds me a lot of this code I saw in a talk by Surma some years ago that's called, whatever smart thing you think you did, game developers did it 10 years ago. And I've already showed two kind of evidences on this, but on the post by Surma, he goes on, this attitude does not only work in the context of the game industry, though. Any other industry with strong architectural requirements can be a source of inspiration and knowledge for us to help write better code on the web. Oops. So for that, I want to talk about entity component systems. And my history of that started a few years ago when I was doing native iOS, so I would play around and build those simple platform games, 2D stuff, or even some puzzles with physics in it. And when I was reading through Apple native APIs, I first saw this thing called entities and components as part of Gameplay Kit. But that's not the focus here. What prompted me into talking about this was this tweet by Jordan Walk, aka the father of React. So last year, he was talking about how the dawn was born of an abstraction around 3 data structures and stuff, and he was wondering, what if things were different? And then one person commented, you're talking about ECS. And then he asked, is this a unit thing? And then they said, no, this is a game development thing. So I was like, okay, it's probably time we talk more about that. So to do an overview, we need to take a few steps back and talk about hardware, because our CPUs are fast. Basic mathematics can be done in a few cycles, and the things that are complex, that we learn in school as complex, like division, square root, and whatnot, they will take a few cycles more, but they are still fast. Not to mention we have SMID, which stands for single instruction multiple data, and this basically allows us to process multiple values in the times of a single instruction. What's not so fast, though, is memory, because our CPUs can only work on the data that's collocated, so physically collocated. That means the register itself, the CPU, or the closest L1 cache. Everything else needs to be loaded. So talking numbers, let's say our L1 cache is less than 1 nanosecond from our CPU. Our L2 cache would be something around 4 nanoseconds ballpark number, and our RAM memory is like 100 nanoseconds. If we're thinking multipliers, that would mean something can take x, something can take 8 times x, and something can take 200 times x. Of course, smart people throughout the years, they came up with alternatives for that. One of them is, for example, called cache prefetching, where basically the CPU tries to understand what is the next thing you need, and then it preloads it from the memory. But overall, memory access is slow, and caching sometimes will alleviate the pain, but that depends on your access pattern of your data. So linear patterns, they tend to be good because they're predictable. Things that are harder to predict, they tend to be bad. Another thing that came out throughout the years to mitigate this is what's called data-oriented design. So data-oriented design, not to be confused with data-driven programming, is this umbrella of techniques where you are analyzing the patterns of the different kinds of data from your application, and you're trying to optimize to better use the underlying hardware. So these are often about optimizing for CPU cache, limiting the amount of things you load and you store from the brand, and also optimizing for SMID instructions. And one of the things you hear a lot in this world is AOS and SOA. So AOS stands for array of structures, and if we were to quickly model here a game, let's say our characters are an entity. And by the way, the slides are online, so if you cannot read it, you'll get to. But let's say we have an entity, and this entity has 3 properties. It has a position, which is coordinates x, and y. It has a velocity, also x, y. And then it has some hit points, because our character can take damage, right, in our game. So our entities would be that array of characters, each one with their position, hit points, and velocities. We're talking about going from this to this. So instead of having an array of each of those, we have an array for all of our positions, an array for all of our velocities, an array for all of our hit points. And we have some sort of ID, which here is an index for us to access each one of them. And you can notice that I'm using typed JavaScript arrays because basically they give me continuous memory layout, and they are more efficient when it comes to size and caching. Plus, they will parallelize better, as we'll see. So the shift we had here was basically going from something that, yes, is easy to read and write and even reason about, because those are just, we learn how to bundle these different properties all together. But we had poor data locality because of the memory limitations we talked about, and iterating with them over all of them were scaled badly. And we went to this thing that has really, really good data locality. It tends to be cache friendly and even easier to accelerate with SMID, but we have something that is overall less intuitive because basically we don't learn to think like that most of the times. But let's illustrate this. Those are the properties we talked about: position, x and y, and velocity, x and y, and hit points. So distributing those over the memory, we have in the first row our first three entities, second row another three entities, and so on, right? Now let's say we have a damage function that will make our character take some damage. This function is accessing and modifying only the hit points. And you can see how things are sparse in between here, right? And overall, sparseness is not what we're looking for. We don't want that. And this is 4 positions sparse, and it can be already bad, but at scale, because at the end of the day, our churches will have more things than just those 3 properties, right? So this is the problem, and this is the problem addressed. So with structure of arrays, we have our first array with all the positions, all the velocities, and all the hit points. And you can even process that across different threads. So that's what data-oriented design is all about, having those small loops of arrays that will operate on those arrays that contain all of our fields, and then we're minimizing the amount of data in cache that is not read or written. So those sparse squares that we saw in the previous example. And thus, we tend to have something that's more parallelizable because they're not sharing the same logical object. They don't share fields. I put together a very, very simple example, which you'll be able to find in this QR code, but it's basically benchmarking the 2 different approaches, array of structures and structures of array. And you can see that things start pretty well. So we're looking at the last column, throughput, the average throughput. And with array of structures, we got 223, and structure of arrays 984. That's better, but not that better. You wouldn't refactor your whole code just for that, right? Maybe you don't need that to be that precise when optimizing for speed. But then let's add more properties. So we had just velocity, position, and hit points. Now, instead of just 5 properties, we have 20. The second approach stands at a solid 975 operations per second, while the first one went all the way down to 10. But let's scale this even more. Now our objects have 100 properties. You can see that the second approach remains at a solid 970, and the other one dropped all the way to 2 operations per second. And I think that this reflection is really important, actually, because I think it's important sometimes that we think about things that thrive when at scale. And here's a totally not related example, but in 21, yet another Ryan Carniato reference. Yes, Daniel? He was comparing and benchmarking the bundle size across different popular frameworks. And Svelte, when you had one component, it was the one with the smallest bundle size. But in the benchmark, as he added more components to the application, to the demo application that was being benchmarked, Solid and then Preact took. And then you can see that when at 8 components, Preact was the one resulting in the smallest bundle size. Does that mean you have to start using Preact for your applications? No. But the overall idea of thinking about things that will thrive in a specific criteria when at scale. Anyways, if you want to check, there's this talk by Stoyan on how to optimize, how they optimized a lot of Chrome rendering with this including FPS and stuff with data-oriented design. It's a really, really great talk you may want to talk about. You may want to check it out. A little bit on the architecture of it, because I promised ECS. So now that we've drafted the whole foundation, basically the architecture of ECS surfaces these three concepts, where basically we have entities that are unique identifiers that can have 0 or more components they can handle. Components are those plain data types that don't carry any behavior, and systems are the functions that are matched with those entities that have a certain set of components. So back to our example, those would be our components, and we're bundling fields into them, and they can be added or removed. Our entities would be this, where you can assign every object in that world, if we're talking about a game with an entity ID, and each entity can have an arbitrary number of components. And our systems would be, for example, taking damage, updating position, plotting the character to the world, and this kind of thing. Wrapping up a little bit on ecosystem, this thing is in a lot of places, actually. Like the games we play. So Unity and Unreal, two of the most popular game engines, they have subparts of it that leverage ECS. Not only that, not only a proprietary software, but also an open source stuff. Entity, which is an open source C++ engine. The thing behind Minecraft, if you know Minecraft, they also heavily leverage ECS. You'll find also a lot of case studies in game development conferences of how people optimize their architecture with ECS, or specific flavors and implementations of ECS that unfortunately I don't have the time to talk about. So this is one example of Overwatch and how they optimize things with ECS. And this is also in the apps we build on the web. So there's Miniplex, which is a fairly popular thing, but also CUDA by Poimanders. If you know, Poimanders is an open source collective with a lot of popular stuff, like a lot of state managers like Zustand, Jotai, and others. And they have been working for the last 1 year or two in this state manager based on ECS called CUDA that you can also use with React. And why does this whole thing matter? I think it's about challenging the status quo, because we learn how to program by thinking about code coupling. We know that we don't want to mix concerns. We know that can be bad for the maintainability, and we often see that as an issue and something we want to avoid. But we rarely think about data coupling and how mixing up the data slices that are not accessed by the same code can be bad for data sharing and for the underlying hardware. And that's not often seen as an issue. So I think this is interesting, because there will be some times where we'll be in positions where we have to think about hardware constraints. For me, this happened twice. First time was when I was building this game that runs behind an actual goal with an actual goalkeeper, and we had very, very limited resources on the LED panels behind this goal. And also when I had to build web apps to run on billboards, because guess what? Those billboards, they also have very, very limited hardware. And it's not hard to find this kind of use cases. Netflix, for example, they have a use case of how they could optimize for smart TVs with very, very specific constraints and limitations and stuff. You might want to check out Flipboard, also has an interesting case. So closing up things, I think that the order of the talks is actually really well put together, because from the first talk by Samo, we start seeing how it's important that we look back to the past, because I strongly believe that, and a lot of you will probably agree with me in that one, that software development is continually going through cycles. So I think we need to always question what has changed from the last iteration of a concept or of an idea, and what just turned into lost art. What are the great things we had, like in 2005, in the 90s, that could be presented today with a different flavor, with changes and with stuff, but they were great ideas. So that's what this talk was all about. This Steve Jobs kind of thing of staying hungry, staying foolish, like always trying to find new sources of inspiration and knowledge. It doesn't matter if it's from a different country, a different industry, a different ecosystem. That's it. Nognufala, I hope I'm pronouncing that correct. The slides are available there, and other talks I have on the web, on the history of the web, in journals of stuff. I hope you liked it. 45 minutes, Daniel.